Hello everybody, it is time for our video on the force of gravity, Newton's idea of what gravity is. This is going to be the most mathematical video that we've had yet. And this is, yes, unfortunately, where I'm probably going to lose some students. My reputation is going to take a big hit. Bear with me. I'm going to give you a template to show you how to solve this, and I give you lots of opportunities to practice. I have even released a practice problem set on Canvas with a template that you can run through of a method that you can get to the right answer for how I ask questions about gravity while reinforcing how gravity actually works. All right, so let's go ahead and jump in at one of the most important concepts we have this semester, the force of gravity. So Newton, in his brilliance, not only came up with the laws of motion that describe how things move, but remember that in all those laws of motion, they basically boil down to that things move when a force is applied to them. And he was obsessed with trying to figure out why Kepler's laws work. Why does the Earth orbit around the sun? The Earth, as it orbits around the sun, is constantly changing its motion, is constantly changing its direction, and it's actually changing its speed if you think about Kepler's second law. So what is it that's changing that motion? And if that motion is changing, there must be a force that's doing the changing to the motion. Newton was obsessed with this, and you can always go with the not true. He got plunked on the head by an apple, and he was, oh, gravity. But no, he did not get plunked on the head with an apple, but he did come up with a concept of why Galileo observed that things fall at an accelerating rate. He came up with humanity's first concept of this universal force called gravity, a force that applies to everything in the universe that has mass. And it says that everything that has mass creates this force, this tendency to move the two masses called gravity. And it works only in one direction. Things that have mass are attracted to one another. So we have one mass here, another mass here. There is a force of gravity between them trying to pull them together. And that's true for this and myself, this and the sun, this and the earth, the sun and a galaxy way over there, a galaxy way over there, and a galaxy way over there. Everything that has mass is exerting a gravitational force, a tendency to try to pull things towards it, to everything in the universe. And it applies not just to here on Earth, but within our solar system, so objects in orbit around the sun, and everywhere in the universe. It is a universal law of gravity. A force generated by everything that has mass that's trying to make every other massive object in the universe change its motion. It doesn't take very long to think about that to realize that, whoa, that is deeply profound. Hopefully that level of profoundness has encouraged you to deal with some equations, because here we go. What is Newton's law of universal gravity? The so-called gravitational force. Remember, forces are labeled with the letter F. So here's the equation. The force of gravity equals blah. So it equals big G, and then multiplied by the fraction of mass 1 times mass 2 divided by the distance between the two squared. So here we have two masses, mass 1, mass 2, measured in things like kilograms. So how many kilograms is this? If you're talking about something like the Earth, 10 to the 24th kilograms, something like the sun, 10 to the 30th kilograms. But it doesn't matter, just two masses, measured in kilograms. Then they're separated by some distance r in space. They're either close to each other, far away from each other. Whatever the distance between these two, we just call that the distance and we label it r. And then we have this big G right here is just a number. In fact, it's a profound number. It is it's a universal constant called the gravitational constant. It has a value of 6.67 times 10 to the negative 11th. The units are meters cubed per kilogram per second squared. You don't need to worry about that though. You don't even have to remember what big G is. Just know that it is a number that assigns how strong the force of gravity is. if the universe worked out a different way and this number were larger, masses would be much more attracted to one another. If this number was smaller, they'd be less attracted to one another. It was just some number, though. If you want to, you can scratch it out and replace it with a drawing of a smiley face. We're never going to use it. I'm not going to force you to use it. Okay, so now we have Newton coming up with this equation that tells us how gravity works. How strong is the force of gravity? And it equals this. Let's break it down. We have this top part. So how strong gravity is depends on, it is the product of the masses. It is directly proportional to the product of the masses. What does the product of the masses mean? Mass 1 times mass 2. So if this is 10 kilograms and this is 10 kilograms, 10 times 10 is 100. So you'd put 100 up here on the top. And then it's inversely proportional to the square of the distance. So how strong the force of gravity is inversely proportional to the square of the distance. And that's the distance between the masses. And anytime that something is inversely proportional to the square of the distance, so if this is 10 meters, the number I'd want to put down here, if these are separated by 10 meters, the number I'd want to put down there is 10 squared, 100. That would mean that gravity is getting 100 times weaker. But anytime something is inversely proportional, one gets bigger, the other one gets smaller, to the square of the distance, we call that an inverse square law. And inverse square laws exist everywhere in the universe, everywhere in nature. Gravity is just one example of an inverse square law. So let me say that again because it's really, really important. I know getting your brain wrapped around these proportional to and inversely proportional to is new. Let me go ahead and walk through it one more time. So how strong gravity is directly proportional to the product of the masses. I double the mass of this one, so it's 2 times greater. I double the mass of this one, it's 2 times greater. 2 times 2 is 4. Gravity would become 4 times stronger between them. I make this one 5 times more massive. I make this one 3 times more massive. 3 times 5 is 15. Gravity would be 15 times stronger as long as the distance is the same. I have some distance between these. I double the distance 2 times farther away. And it's how strong gravity is inversely proportional to the square of the distance. Double the distance, 2 times more distance, 2 times larger, but gravity is inversely proportional to the square of the distance. 2 squared is 4. Gravity becomes 4 times weaker. Let me say that again. Double the distance, 2 times farther, 2 times larger distance, square it, 4. Gravity would be 4 times weaker, 1/4 as strong. Triple the distance, 3 times farther away, 3 times greater distance. 3 squared is 9. The force of gravity would become 9 times weaker, 1/9 as strong. There's the same thing that I'm saying there. 9 times weaker is the same as 1/9 as strong. Make these things 10 times farther away from one another than they were. So here, and move this 10 times farther away. Gravity would become 10 squared, 100 times weaker, 1/100th what it was before. And that's the power of this inverse square law. Gravity gets weaker with distance really, 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 really fast. Take these 2 objects. Now let's go the other direction. Now I'm going to move this 2 times closer. So the distance is 1/2 what it was before. 2 times closer, 1/2 the distance. So this 2 times closer, 2 squared is 4. Gravity would become 4 times stronger. Okay, hopefully all of that is starting to make sense. Just to walk through that again, I can't say this as enough, so I'll say it as many times as I can and hope that it sticks. So what does it mean to be inversely proportional to the square of the distance? What is up with all these inverse square laws? How bright objects are, how bright stars are, how far is inversely proportional to their distance, how bright we see them to be. How strong the electromagnetic force is an inverse square law. These things are everywhere, so it's good to take some time to understand what an inverse square law is. Gravity is an inverse square law. So the easy way to say it without a whole lot of mathematical legs is as distance increases, gravity decreases a lot. Inversely proportional, as one goes up, the other one goes down, but now we're throwing in a lot. What do I mean by a lot? So if the distance becomes x times larger, so distance is larger, gravity, force of gravity would be weaker, but it would be x squared times weaker. So you always got to square it with an inverse square law. And remember that it's inversely proportional, so if one got bigger, the other got smaller. If one got smaller, the other one got bigger. So let's go through that. As distance decreases, gravity increases a lot. What do I mean by a lot? So the distance becomes x times smaller. They get closer together. The distance is now smaller between my hands. That's 1 over x, the original distance. And then gravity would become x squared times stronger. All right, let's do another example. Let's consider two masses, two stars, or a planet star, whatever. These two balls. And what I'm going to do is I'm going to make the distance to be 5 times greater between them. So I've made the distance 5 times larger. 5 squared is 25. Gravity will be weaker, and it will be 25 times weaker, 1/25 as strong. If I move them to be 5 times closer together, so now the distance is 1/5 what it was before. 5 squared is 25. I know since the distance got smaller, gravity got stronger, that we get 5 squared 25 times stronger. All right, so how are you going to work with this? Because notice that I said that I'm not going to have you solve equations or things like that. So how am I going to actually see if you're understanding how gravity works? And the way that I design all the questions in this class is to exploit this proportional to, which means that we're going to compare one scenario to another scenario because they're changing in proportion. If you compare them, you can do them in proportion to one another. You need 2 scenarios to compare to do these proportions. So we could call them scenario 1 and scenario 2, but that sounds really abstract and doesn't feel like it has a whole lot of meaning. And it's a lot easier and it feels more natural to say a before and after scenario like I was doing here, where I have the before scenario where we know we have this mass, we have that mass, and then we change the distance or we change the amount of mass. So we have what it is before, that'll be our standard. Then we're going to change things up and see how gravity changed in response, the force of gravity changed in response to changing how much the masses is, changing what the distance between them are. And now, bear with me. I'm going to talk through this. You'll never have to do something like this, but I want to talk through this so you can see that where I'm going to have this template that I am giving you, where it comes from and how to go through it. So I just wanted to go ahead and show you the brute force way. And then I'm going to show you a much, much, much easier way so you can breathe a sigh of relief and realize that you never have to go through all the mess that's on this screen right now. Okay, so let's say we have a before scenario and an after scenario. I'm going to put a big B up here to remind myself that these are the before numbers and a big A up here to remind myself these are the after numbers. And I'm going to color code it as well, where all the after stuff is in red, all the before stuff is in blue. And what I'm going to do is I'm going to have a scenario, mass 1, mass 2, separated by some distance, and then I'm going to change it. So here, I'm going to say that this ball right here weighs 100 kilograms. Obviously not, because I would have trouble picking up 100 kilograms, if I even could. Don't want to find that one out. So let's say this one's 100 kilograms, mass 1. This one is 500 kilograms. I'm going to change it where all of a sudden this 100 kilogram one, we're going to make it 300 kilograms. So we'd have 3 of them. And let's take 4 of the 500 kilogram ones. So it changes and now it's 2,000 kilograms. So had the original ones and then I just add a bunch of mass to each one of them. And then I'm going to take the distance between them and I'm going to make it 10 times larger. Let's actually track those changes. So if I'm going to make this one 300 kilograms, that's 3 times what it was before. That's an important thing to note, that this is really 300 kilograms is just 3 times 100. So this is 3 times what it was before. 2,000 kilograms is just 4 times what it was before. Oh, sorry, and I'm going to increase the distance to be 6 times. Sorry about that. So I'm going to take the 10 meters and I'm going to change it to 60 meters. So it's going to be 6 times what it was before. Now I could use the force of gravity equation and I could crunch through all the numbers. I could put in the value for big G, put in the value 100 kilograms, 500 kilograms, 10 meters, and I could multiply across the top, square this, and then divide by it. And calculate, 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 calculate. Hope I put everything in my calculator correct. Hope that I keep track of all my squares and everything else in this 10 to the minus 11. And if I'm careful, I can come out and I can get a real value. I can figure out what the force of gravity would be for this scenario. I can calculate it. It would come out to be a number that's 3.335 times 10 to the negative 8th newtons. But clearly, that is not something that you want to be forced to do on an exam when you're under a time pressure and mistakes are not allowed. Just like you wouldn't want to do the same thing in the after scenario, where I could go ahead and plug in all the numbers, put the big G, 6.67 times 10 to the 11th. Now this mass is 300 kilograms. This one's 2,000 kilograms. The distance is 60 meters. Square that. So multiply across the top, divide by 60 squared, multiply by 6.67 times 10 to the 11. Calculate, calculate, calculate. Don't make any mistakes, by the way, because that's not good. And you come out with 1.11167 times 10 to the negative 8th newtons, which I can even reality check, like, is that the right number? Yeah, I guess so. Don't really know what that means, but that was what my calculator said. That's not a whole lot of fun. You could crunch through all of those numbers, probably get a headache, and curse Dr. Lindsay's name from now until the day that you die, and then get even more upset whenever he goes, well, how is gravity different between the after scenario and the before scenario? Is gravity stronger or is it weaker? And you go, well, that's a smaller number, so gravity's weaker. Well, how many times is it weaker? And you're like, Dr. Lindsay, there's a special place for you in hell for all this mathematics, and you should maybe just go hang out there. Or you could just go, all right, fine, fine, fine. If you're gonna force me to do it, I'll take the two numbers and divide them. I wanna know, okay, the force of gravity after divided by the force of gravity before equals this number divided by this number. Oh, it's 1/3. So gravity got, it's 1/3 what it was. So from the before to the after, gravity became 1/3 what it was before. It's 3 times weaker. Are you happy now? And most people are probably not very happy because that was a lot of work just to come up with a number of gravity is now 3 times weaker, 1/3 what it was before. We all got a lot of headaches, and I'm not even sure that running through this over and over and over and over again really teaches the concept of what gravity is. I'd like a different method, one that's easier for you and more meaningful just in general. So there is an easier way to do all this. Let's look at how I set it up before. So I had my masses and my distance before, and notice that I tracked them. This was 3 times what it was before, 4 times what it was before, 6 times what it was before. Here's my force of gravity of before. Here's the force of gravity equation for after. But now, instead of putting all the numbers and crunching them, let's just go ahead and say, oh, well, this is just 3 times the before mass. This one's 4 times the before mass for mass 2. And the distance is now 6 times what it was before. Notice that I've color coded and used those letters to hopefully key into your brain. Gravity, or the gravitational constant, didn't change. Big G is still just big G. So now I have that the after, let's just go ahead and pull these out front. 3 times 4 divided by 6 squared. And collect all these terms over here. We have big G, mass 1 before times mass 2 before divided by the distance between them before squared. Wait a second. This number right here, that's exactly the same as this right here. That's just the before case of how strong gravity was. And now I just have these numbers over here. Okay, let's multiply across the top. 3 times 4, 12. 6 squared is 36, 6 times 6. Times, just get rid of all this gobbledygook and just write that as, oh, that's what gravity was before. And I can divide 12 by 12, get 1, 36 by 12, get 3. Oh, gravity is just 1/3 what it was before. Done. I just need to see how things changed and then work my proportionalities that's directly proportional to the product of the masses. 3 times 4, that was the change, and inversely proportional to the change in the distance squared. 6 times bigger distance, 6 squared, 36 times smaller, 1/36th what it was before. Nice and easy. Let's codify this because I have a nice little template. Notice that here I put all the numbers out front. Now I'm just going to use some boxes. So whenever you use my template, I'm going to show you what it looks like. You can go download it. It's on Canvas. I'll put a link to it right below this video and week 5 module as well. So let's go ahead and take a look at what you'll see and then the method that you can go through this so that hopefully all the work that you do with gravity becomes a lot easier and you're working in a more meaningful way. You're understanding what gravity depends on. It depends on how you change or what the masses are. It depends on the distance between them, and it depends on the square of the distance between them. So I'll always set it up where you have a before scenario, and this is how I'll do it on exams as well. So exam 1 coming to you in about 2 weeks. This is and then I'll change things to an after scenario. But the way I'm going to do it is we have the mass, and I'm just going to tell you how much it changes by. So mass 1 changes by put in some number here. Mass 2 changes by put in some number here. The distance changes by put in some number here. And then you can just keep track of these boxes. I put them down here. So whatever you put in these boxes up here, it's just sort of a bookkeeping thing. You'll put in these boxes down here. So notice that for the change in masses, the force of gravity is directly proportional to the product of the masses. So you just multiply across the top, directly proportional to the product of the masses. So if this is 3, this is 4, you'd put 3 times 4 is 12 here. And if this was 6 like it was in the previous one, you'd put a 6 here. 6 squared is 36. And it's inversely proportional to the distance squared. That's why this is down here on the bottom. Distance gets bigger, you're dividing by a bigger number, this gets smaller. Inversely proportional to the square. And I know that m1 times m2 divided by r squared. Oh, that's just what I had in my before scenario, so get rid of all those and just put the before. And then an extra little box so you can go ahead and reduce things down to a nice simple format. So I'll always give you a before, tell you how I'm going to change the masses, change the distance, and you tell me the after. No, video is not over because it'd be unfair to just leave you there. I should run through some examples, and I think I might not update the numbers up here, but this is example number 1. So I'll tell you something like, hang on, I got to move some things on my screen so I can see. And it's a little bit easier for me to talk then. So mass 1 will become 3 times larger. Mass 2 becomes 4 times larger. The distance becomes 6 times larger. That's kind of the words that I'll give you to solve the questions. I'm not going to try to disguise these from you because I shouldn't disguise things until well, I should never disguise things, but I should give it to you in the simplest way so you can learn how to do this in a nice, simple, controlled way. So mass 1 becomes 3 times larger. Notice this is the example before, so I'll put a 3 here. This becomes 3 times larger, so it's 3 times what it was before. Mass 2 becomes 4 times larger, so it's 4 times what it was before. And the distance becomes 6 times larger, 6 times what it was before. Now, all I have to do is take these numbers and put them down here. I want to know what the gravity is after, so I have my 3, my 4, and my 6. Then I'm going to multiply across the top. Gravity is directly proportional to the product of the masses. 3 times 4 is 12. And then I'm going to square the change in the distance. 6 squared is 36. So now I have 12 divided by 36 times what gravity was before. And I can reduce that. And I realize that gravity is 1/3 what it was before. Gravity has become weaker in the new scenario, in the after scenario. is 3 times weaker than it was before, which is the same as saying it's 1/3 what it was before. All right, example 1. Example 2, mass 1 becomes 100 times larger. Mass 2 becomes 2 times smaller. What does that mean? It's half as large. 2 times smaller means half as large. So divide that number by 2. So it's 1/2 what it was before. And now the distance between the two objects will become 7 times larger. Okay, I've done my bookkeeping. I have my numbers up here. I translated the information I gave you into the template. Now I just have to copy those numbers down here. The mass 1 goes there, the mass 2 goes there, the distance 1 goes down here on the bottom. So 100, 1/2, 7. Now I'm going to apply my directly proportional to the masses, multiply across the top. 100 times 1/2 is 50. So 100 divided by 2 is 50. 7 squared is 49, so divide by 49. And I'll get that gravity is, oh, that's a little bit stronger, but not much stronger. It's 1.02 what it was before. It's 2% stronger than it was before. Notice that I can also tell it is going to be stronger before I even got to that last step. Because the masses here are making gravity, if you just consider each one of these dependencies independently, then the masses, in this case, are trying to make gravity 50 times stronger. The increase in distance, however, is trying to make gravity 7 squared 49 times weaker. 50 times stronger is greater than 49 times weaker. So overall, gravity will be stronger. And the ratio of those, 50 divided by 49, will tell you exactly how much stronger. 1.02 times stronger. All right, example 3. Now I'm going to make mass 1 be 5 times smaller. That means 1/5 as large. So 1/5 what it was before. Mass 2 is going to become 75 times what it was before, 75 times larger. And the distance is going to become 5 times larger. I've done my bookkeeping here. Just translate the numbers down here. So 1/5, 75, 5. Multiply across the top. Product of the masses, 1/5 times 75 is 25. 5 squared is 25. 25 divided by 25 is 1. Oh, in this case, I changed the masses. One got reduced to 1/5 what it was before. The other one became 75 times stronger, or 75 times larger. And then I increased the distance by a factor of 5. An entirely different scenario, different masses, different distances between them, but the same force of gravity. Because you can see how the masses and the distances are playing off one another. So in this one, there would be no change. Gravity would be the same after as it was before. And example number 4. All right, so now mass 1 is going to become 8 times smaller, 1/8 what it was before. Mass 2 is going to become 120 times larger. And I'm going to switch things up. And this time I'm going to bring the masses closer together. So the distance between the two objects will become 3 times smaller. It would be 1/3 the distance. So the distance is 1/3 as large as it was before. It's 1/3 the distance. So the distance is 1/3 its original value. Just do my bookkeeping. 1/8 here, 120 there, 1/3 down there. Multiply across the top. 120 divided by 8 is 15. 1/3 squared is 1/9. Remember that if you divide by a fraction, 15 divided by 1/9 is the same as 15 times 9. So you'd flip this and you'd end up multiplying by 9. And 15 times 9 is 135. So in this scenario, gravity becomes 135 times stronger. Now, I've worked through some examples. You have some more that are different in the lecture slides, in the Unit 1 Part 3 slides, and you have a practice problem set to work with, and you have some in the homework to work with, so there's plenty of practice for you to start mastering this. But I want to introduce you to the template. So this is what you can download. It's a sheet of paper that looks like this. Has some explanation to help you through. It's mostly what we have been going over for the last while. And then here's that bookkeeping part where I have Mass 1, Mass 2. I'm going to change them, and here's the blank boxes for you to fill in. And then you're just going to take what you put in these boxes, put them down here. What you have in this box, put it down here, multiply across the top, square the number on the bottom because there's the square right there, and then figure out if gravity is going to be stronger or weaker than it was before. So the exact same thing. This is the template you can work from. You can go ahead and print it out. The one that I provided is two-sided, so you get two for one piece of paper. Or you can just go ahead and start drawing out your boxes yourself, or come up with whatever method works best for you. And if that method is working right for you and you're always getting the right answer, I'm not going to argue. If you're getting the right answer, you're working towards understanding what's going on, and I'm a happy professor. All right, this was an extraordinarily long video. Thank you for tuning in. Hopefully you can go rewatch this for examples, and it'll be one of the more useful videos. And hopefully what was one of the scariest math parts of our class doesn't feel as bad anymore. All right, thank you for tuning in. I will see you in the future where we still have some more math because we're going to be playing with gravity.